Gakis. He's head of Geotechnical at Dr. Sauer and Partners. He's got an academic background with a BSc and an MSc, and then a PhD in civil engineering, initially from Greece and then from London from Imperial College. Chartered civil engineering in the UK. His working experience includes 20 years of geotechnical tunnelling design and site supervision in both urban and rural environments. Since 2011, he's been working with Dr. Sauer and Partners in the UK on major projects and international projects. And in 2019, relocated to Salzburg office, major projects, and has been involved in holding senior roles, including other projects like Crossrail 1 and 2, light rail in Toronto, and Metro M2 in Tel Aviv. So over to our three presenters for this evening.
Okay, good evening all. Thank you for coming here tonight. We're going to present the Highway 401-409 rail tunnel construction in Toronto, Canada. It's a very nice, quite small project, but very interesting. Had a few interesting aspects for us that were quite challenging in the design. The project overview, the project client is Metrolinx, an agency of the Government of Ontario, together with Infrastructure of Ontario, the Ministry of Infrastructure. We were the Toronto Tunnel Partners, a joint venture of STRABAG and Elliston, a local Canadian contracting company, and the construction joint venture and financing joint venture hired WSP, Sauer and Partners, and Wood to provide the engineering services required for the project. The overall scheme was a design, build, and finance contract. Contract value about 120 million Canadian dollars, so that is probably 75 to 80 million pounds. The reason or the purpose of the project is enlarging capacity of a commuter rail line from the northwest of Toronto into the city of Toronto, and a part of that capacity enhancement is this 180-meter long underpass under the two highways. This is the location of the tunnel. If you know Toronto, downtown Toronto here at Lake Ontario with the CN Tower and all these things, Pearson Airport over to the west, Highway 401, here the 409, this little scratch, and this is, if you are in Toronto, that's where you're going to sit in a traffic jam going from the airport to the city. So here we see it, Highway 401, 18 lanes of highway, express lanes, commuter lanes, and the intersection, one of the busiest stretches of highway in North America, 450,000 vehicles a day in this stretch. And that is the situation. Here you see the highway, the existing commuter rail line with 3 tracks of rail, and they needed another 2 tracks to increase capacity. Gerhard will talk to you now a little bit about the contracting models that were under discussion and which one was chosen.
So good evening also from my side. Thank you for the opportunity to provide this project presentation today. You will see it's a small project, but we believe it's worth the time looking and listening to it. We went through many challenges on this project from start to finish, but we finished successfully at the end, and we want to take you through on this journey and be part of this journey. Thomas already outlined the project in general, so we were asked to build 2 tracks of railway, basically under, it's actually 21 lanes of highway. So it's really a busy highway, which we were not allowed to close down, no lane closures allowed and so on. So that's why we had to look for for innovative tunneling solutions. For us as a contractor, it's always important also what is the contracting model for such an undertaking. It seemed to be obviously a high-risk project because live traffic, which cannot be interrupted, you will see the conditions left and right, very, very challenging. At the end, we accepted this design, build, finance model with the client, Metrolinx, put on the table. It's very common and popular in Toronto, so they use this model a lot. For me, not logically understandable too much, I have to say, because the financing aspect of this contract model requires that it's basically set up like a PPP project, a public-private partnership or PFI project. So you need all the contracts, all the regulations, all the financing, all the rating agencies and so on. Everything you need for a PFI project, you need for that, for this design, build, finance project. You build the project basically and you get paid at the end at substantial completion and by the client. But it's an established project. Metrolinx has awarded about 100 projects with this model. We have gone through a few of those, so we were used to it, and that's why we accepted this as a design build, first of all, project with a high risk profile, and the finance aspect as well. That's why we also had the local partner, LS Don, who supported us on that. The procurement itself was started with a contractor outreach, was very interesting. I once got a call from a Metrolinx person, a project manager, who approached me and put a sketch forward and said, we need to build it. That's our idea, how we should build it. Is that buildable? I will just, in the next slide, show you where we started off with. We then went through a pre-qualification process, typical these days, and then through an RFP process, which was taking more than a year to go through this development phase with the client, basically. And then there was an evaluation, 50-50 more or less, price and technical. And then at the end, we got the award as the best consortium, basically, in the process. Clients in Toronto going through these projects also provide a stipend, which means payment for the unsuccessful bidders. In this case, it was $400,000. Not a lot when you think you work for 1 year with staff, designers, everybody around to develop this project, but at least it covers some part of the costs, and we always encourage clients to do that, obviously, because it's a big investment for everybody who gets involved to get at least some of the costs back. This was the sketch that I got approached with. You see on the left side, the green structure is the existing tunnel. It's an open cut box construction. It was done in the 60s, 1960s. And they needed 2 more tracks, and that's what was the idea, how to build these 2 more tracks. As I mentioned, there's the highway on top, 21 lanes. The distance is about 2.5 meters on top of the tunnel. The settlement criteria, we're going to talk a lot as well, it was very, very tight, and the idea was from them to have drilled piles basically around the tunnel circumference and then push a box through this structure. A method we very soon found out doesn't make sense at all and doesn't work. But they were open to talk with us about it, and we could even, before the RFP or RFQ came out, they adjusted the contract requirements and specifications and opened it to more options, more technical options that we use then also to develop the project.
Okay, I will take you now through this bid process that Gerhard described. It was a lengthy process. We got presented, as he said, a reference concept design where we saw some major problems with and some challenges that were there that we had to find a solution for. The problem was the low overburden. The existing tracks, the tunnel had to, or the new rail lines have to tie into the existing rail lines. There's a station a few 100 meters to the west. There are bridges a few 100 meters to the east. So to eliminate, we needed oops, sorry, the major challenge, the clearance. We needed to make the tunnel as compact as possible. In the contract, initially they required interlocking pipes as a pre-support. As they had both tracks in one tunnel, the span in this box got massive with the steel, and they required a concrete support, the installation of the waterproofing. They had requirements that was really difficult. Another issue with the pipes was, and Gerhard is certainly talking about that later on, pipe jacks would be straight, but the alignment was curved, so if we have to jack straight, the tunnel got even wider. In order to shorten, there was this shaft in the center. We couldn't close any lanes, or only under massive financial burden. The settlement criteria they presented to us were quite stringent. They changed several times during the review process or during the bidding process. So we had settlement criteria on the road, on the existing tunnel, and on, for instance, this retaining wall that we see here in the model, and it sits here because the ramp of the 401 is coming down. To start with, we had settlement criteria of a review level of 0 millimeters, an alert level of 0 millimeters, and a stop level of 1 millimeter. So we had to work quite a lot on explaining to the client what is useful and what is helpful and what we can and cannot achieve. Another aspect that we also needed to negotiate away, if you wish, is they also had a criteria that these pre-support pipes, they would need to be installed with a pressurized phase TBM through this artificial fill, where we also saw major problems with it. During the bid process, we assessed various options to perform this. We left the pipe support and tried to reduce the span by introducing additional columns in between the two tracks. Made it, again, with straight pipes, the tunnel larger. We tried to do a curved roof that would have a certain compression in it, and with a tension tie in between. We tried to move the box closer to the existing tunnel to make alignment easier. We looked at the pipe, the box checking option that was the RCD, and thought about how to do that. And we also looked at two options for the an NATM SCL tunnel, one large tunnel that was originally required in the project requirements, and two SCM tunnels next to each other. We evaluated all these options based on their risk, on the schedule, on the construction cost, and the problems that we would expect during construction. And we ranked them and found that the SCM twin tunnels next to each other seemed to be the most ideal option for us. The tender itself was guided, or we guided the process with the client in the form of, they had these design progress meetings. We had 4 of these meetings within the actual tender design periods, and we collaborated with them and discussed all these elements in terms of what settlements. They were very worried, settlements on the road, settlements on the structure, how can we mitigate, and we presented them the solutions. They gave us feedback, and at the end we came up with the selected option. We, from the RCD, from the box with the steel frame, we ended up with 2 SCM tunnels side by side with large diameter, 800 millimeter diameter steel pipes. Originally we planned it to do from the portals, and then from the retaining wall that we showed where there are steel piles as support. From there on we would do a pipe roof section, a regular 138 millimeter pipe roof and go towards the other end where we also installed the large pipes from the portals. Some other elements that we designed out during the tender process: the tunnel is 180 meters long, and originally the client thought we would use mechanical ventilation for the tunnel, for the fire case. We provided them with a CFD analysis and could show them that with a cross passage in between, the smoke evacuation over this short tunnel would work without the mechanical ventilation, and got rid of that aspect of the project. And I said one of the major problems was the pre-support, and Gerhard is going to tell you the hoops we had to go through to get that through.
So the pre-support, you all know pipe arches, and there are different sizes of pipe arches. We knew because the tunnel was going basically through the embankments of these highways that were going on top. And part of it was also fill material, which we will see later. So we knew there are lots of disruptions and things in this embankment that we wouldn't know about and we would encounter during the pipe installation. So we went away from the original 138 millimeter pipes from the regular pipe roof umbrella to something bigger, and we found the diameter of 800 millimeter sufficient to make it an accessible pipe in case we encounter any disruptions in there and we can't continue pushing the pipe into the ground, so we can remove the objects and continue pushing in. One big issue with the client was they specified, as Thomas already mentioned, they specified closed face machines, basically. Anything we would do under the highway would need to be a closed face machine with slurry or EPB mode or whatever. We were of the opinion that just an auger machine is much safer and provides much more control, settlement control, of the material that we would transport out than any closed mode machine. And that was a big debate with the client. They wouldn't want to accept that. So we had to, with the manufacturer of these pipe checking machines, they're based in Germany, we arranged a test basically there in their facilities, brought the client over, a whole group of client people over, and demonstrated that auger setup can be achieved and can provide also the settlement criteria and restrictions that we were given. Only after almost 7-8 months of this kind of convincing process, we were then allowed to go forward with the design of this pipe roof. We will see a few photos later on. It was still not without issues, obviously, but we knew it. There are things in the ground that we encountered, and lots of them, but we had means and measures to deal with them and to work around them. Going to the design.
So, also from me. So I will take you through the design and the analytical part, explaining basically how all these concepts were developed and were assessed and validated. So here you see the first idea of pre-support on the left side. That was our 60% design, as Gerhard and Thomas mentioned. So the middle part was supposed to be pre-support with a conventional pipe umbrella. At the same time, during this design development, the tunnels came closer, became larger, and finally, after a lot of risk assessment workshops, it was decided in the IFC that you see on the right side to cover basically the whole tunnel with a continuous pre-support with these large pipes. That required this intermediate shaft, and of course required a lot of work to be redone to validate the new concept. So in the profile and the plan, it's the first thing that is very interesting to see is that the alignment, both the horizontal and the vertical alignment are not straight. The cover has been reduced to the minimum it could be really. And the two smaller cross passages that were introduced in the middle developed this final concept, the final solution for the project. There were a lot of challenges. You will hear quite often about the low cover. This was really limiting, not limiting, it was low but doable. Of course, we had to take care of the assets of the highway and the existing tunnel. Both remained operational the whole time during the construction. The two sprayed concrete tunnels came extremely close to each other. So in some points there was no pillar. They were actually in contact. And in some cases it increased to about 30 centimeters. And on top of that, the ground conditions, as you see in this indicative section, were not great. So the upper part of the tunnels was excavated in this artificial fill. This was an embankment fill, so it was not terrible, but the engineering properties were extremely low. The bottom half was in the in situ glacial till deposits, but also not great. And yeah, the cherry on top was the backfill on the sides of the existing tunnel, which was a very poor material. And all of these units made the concept very, very difficult. As you can see in the table, I indicatively show the properties from the geotechnical reports. So the primary compression modulus was 10 megapascal and 35 megapascal. I will explain later that this also made the analytical work extremely difficult. And of course, we had a lot of other assets to assess, like the existing wing walls. One of the major assets is what Thomas mentioned, this retaining wall of the 401 ramp, and some deep foundations. So another unique aspect of this project was that a 3D FE model was required already at the tender stage. So we developed what you see on the screen with not the highest level of accuracy, but still quite elaborate and intending to prove the feasibility of the concept of conventional tunneling, assessing essentially mainly the impact to the operational tunnel and the highway. And we also looked at the piles of the ramp. Then we moved to the 60% after the project award, of course. And the main requirement was to basically simulate everything. So you can see the resemblance between the B model and the FE model. The level of detail was extremely high. We had to simulate all the construction steps. And of course, all the assets. But the concept changed. So after a good month making this first numerical analysis work, we had to introduce a shaft, change the pre-support, and this is basically the structural part of the last model that we used. Also, the model was not intending to design the shaft, but the shaft had to be simulated. The construction process had to be simulated in order to get a good initial stress state. Yep, a rather big 3D model, about 1 million elements, 460 steps. This model was really impressive, but after a point we started wondering if it is useful, because the more detail you put into a model, the more difficult it is to understand it. And I think we, at some point, reached this point where we said, okay, no more detail is added. We used also advanced material models for the soil and for the liner. So the final lining was not simulating this model. It was only the initial lining. So we used the hardening more Coulomb because I will show you some sensitivity checks that we did that provided them a better understanding of the ground behavior due to incorporating the unloading modulus. And for the lining, we used a concrete damage plasticity model. The main reason being to not overdo it with the reinforcement and to reinforce basically only the areas that we really had to. And all these things also made the model extremely slow. But what was really useful, and I think the project could have been designed with that because essentially it was a two-dimensional problem, to its most extent, was this 2D model. It's actually a 3D model, 1 meter long. The reason for that was to be able to use higher accuracy of contact and to use a concept for the simulation of the pre-support in the out-of-plane direction. And this model we used to do a lot of sensitivity checks, and we also used to do it some of the additional design checks that were required, like the earthquake design, the final lining design. The main things that we assessed were, in the sensitivity part of it, were the impact of the K-naught, because we received a range, of course, and based on this, we designed, I will talk about that in the next slide. We checked the different material models. What you see here that was very important, the inclusion of this very poor backfill on the two sides of the existing tunnel. And indicatively, I'm showing you here the results for the two different K-naught values for the minimum and the maximum. So essentially, with the minimum, we got about 2 millimeters higher settlements. So we adopted that also in the 3D numerical analysis. And yeah, similarly, the impact of the backfill was something that we could not ignore. So it had to be also simulated. The difference here is again about 2 millimeters higher settlements. So another requirement was to assess the fire impact, the impact of the fire load. The load itself is shown in this magenta dashed line. So we had to simulate 1200 degrees Celsius fire instantaneously elevating and then maintaining the fire load steady for 120 minutes. For that, we used Eurocode. We used Eurocode for the thermal conductivity and the specific heat because, yeah, it is one of the best resources, and the Canadian standards did not provide something similar. And we developed a simplified analysis with a heat transfer without coupling the stresses, which essentially showed us this is the thickness of the final lining. It's about 30 centimeters. And assuming that concrete remained functional, retaining its structural capacity below 400 degrees Celsius, we defined this zone here of about 60 millimeters that was considered sacrificial, not part of the permanent structure. Of course, this was an accidental case, so it was not combined with earthquake design, etc. Useful to say also that the earthquake loads were quite low, so it was not a governing design case. Another thing was going through this ramp and cutting down the piles. We had to transfer the loads or the design loads of the piles onto the initial and the final linings. So we also developed some models to assess these loads. Another interesting part, taking what Gerhard showed before, we did the trials to understand roughly the settlements coming from the installation of one pipe. We back calculated that. We ended up with a volume loss of approximately 1%, and then superimposed all the pipes and derived the final contour plots using this as additional information. Yep, we also designed the but that was rather a conventional soil nail wall. The permanent portal with this interesting geometry was another model on its own in order to understand how we're going to reinforce this thing. The only rather complex thing here was the connection between the portal and the final lining of the tunnels. And going back to the 3DFE, what you see here is basically the zone of extreme strains, or the plastic zone in between the two tunnels. This made the model extremely slow, so the convergence for whoever is working with finite elements was very painful. We managed to speed it up by introducing an additional, not an additional step, but during the excavation we simulated also the application of a thin sealing layer, and this made our lives easier. So the plastic zone that you see here in red is not extreme, but still it was something to deal with. A rather unique requirement by our reviewers was to check face stability and roof stability, albeit the tunnel was fully supported by these huge piles, so we did that. The safety factors were extremely high. What we did here, basically in the Abacus 3D analysis, we manually did a shear strength reduction to get an estimate. And the final results of the FE analysis, of the 3D FE analysis, assessing basically the settlements of the highway at different stages, at the end predicting that the settlements due to tunneling alone would be less than 15 millimeters. And similarly, and very equally important, the impact to the existing tunnel. As said, both assets were operational. We had to make sure that they will remain so. The impact was assessed to be negligible, and I think we also overestimated in the analysis. It was really minute.
So we had a lot of colorful graphs and evaluations and sensitivities and so on, and now the fun part was supposed to start, construction. As you can imagine, there were a lot of people very nervous before we started doing that. One requirement in the contract was that we had to monitor the surface, the road surface of this 21 lanes of highway for 6 months to create a threshold, basically, before we start mining, to see the natural movements compared to the induced movements by tunneling. How did we do that? We installed 3 total stations there, and in the medians beside the highways or between the highways, and monitored right to the road surfaces, which was a very tricky undertaking, as you can imagine, because there's 350,000 people, cars traveling every day. The chance to hit the road actually with a beam is not very high. But the frequency we used and the methods we used also to filter out the measurements that were not usable was at the end very useful and usable, so that we could actually really see the movements if they occurred. We had given ourselves a requirement that in the zones where we are actually excavating the tunnel, we make an increased frequency of measurements just to see earlier if something happens, if there are some settlements, and that we would be able to close down a lane of the highway early enough to avoid any serious accidents or anything more serious even than that. With an interesting discussion, because the specifications required us to do continuous monitoring, and our first approach was that monitoring every 12 hours, every day, 7 days a week is continuous monitoring. As you can imagine, the client was not completely satisfied with that approach, and so we negotiated obviously a more tight schedule also for our own benefit, of course, but as you can see, it's often how you see things can be seen from different sides. Here you can see just another 3D sketch from that. At the end, we measured every 5 minutes and had a lot of data available, too much data, which, as I mentioned, we tried to filter out as well. We used every day in REST meetings to discuss the results, to discuss the movements, and see if we need to change anything in our progress. We also installed inclinometers, horizontal inclinometers. The plan was to install them from both portals. You can see the blue dotted lines to see if there are settlements between the tunnel and the road surface. The problem was that the road surface is a 20 centimeter concrete slab, and you would not see any settlements immediately when the ground settles below the concrete slab. So we had these inclinometers below the concrete surface of the highway to see those movements early enough as well and to be able to react if something happens. Upfront information from the end, the settlement that we actually achieved. We heard the requirements were very strict. You see some dark red zones in there as well, some movements that were beyond allowable limits, I would say. Most of them are around the shaft, the center shaft, you can see there. And the reason was that the sheet piles that we had to put in there between the highway lanes caused basically the settlements to do vibrations of putting the sheet piles in. So it was not the mining or the excavation or the shaft building, it was the sheet piling actually that created that, and we remediated those before we started mining them. But the tunneling you see is very well in the range. There were some areas where we hit obstructions, where we had some more or higher settlements which we encountered for. We had a REST process, what is typically for an ATM, SEM tunnel operation, where every morning we sat together with all involved responsible parties, with the client, obviously with our designer representatives, with the highway representative, MTO, who long refused to participate. Nobody wanted to take on any liability in that phase, but at the end they contributed very well to the process. And obviously representatives from us as the contractor, and we discussed any movements, any settlements, any changes we would need to do to the excavation process. Very fruitful process. So the installation of these 800 millimeter pipes, probably just a short story to that. The original design foresaw spiling instead of any roof pipes. We had long discussions with Thomas, with the whole team, also within my team. At the end, for risk management purposes, I would say we decided to go away from the spiles and use really a pipe arch. We're still debating if the spiles would have worked. We have not found out, and we will never find out. Technically, they would have worked probably well enough, but these big steel pipes just made everybody, also the client's engineer, feel much better about this operation. There were quite a lot of challenges to pressing these pipes in. So these were jacked pipes. We used the same system at one of the projects we constructed in Singapore, a pedestrian underpass. So we had some in-house experience doing that. Obviously, every geology is different, every environment is different. So we had our challenges there. The pipes were at the lengths on the portal sides of 12 meters, and were always pushed in 12 meters, then welded the next piece and pushed in for 12 meters again. In the center shaft, what we see here on the right side, we had two shorter jacking machines in there, and we used 4 meter long pipes, which we added then every 4 meters and pushed them in again. As you can imagine, the challenge is obviously that they are going in the right direction, more or less exactly in the right direction. We achieve that often, not all the times. what we see here is on the right side what came out of monitoring of these pipes. So we surveyed all the pipes that we put in. What we see here going across the tunnel is this retaining wall with the foundation piles, so we couldn't get through those. Those were obstacles we knew that we couldn't get through. So we were spiling in this area afterwards when we mined through. And we also see on the left side there were steel pipes, steel piles that we had to go through and so on. So there were lots of obstacles we had to dig our way through. Looking at the whole tunnel section, the whole 180 meters, you see some green spots in between. But as I said, we were prepared for that, and we had lots of means and measures to fill these gaps, grouting from the pipes or spiling from below to bridge those areas before we excavated the tunnel itself. The tunnel excavation itself was done carried out first with the tunnel on the right side, which was a bit further away from the existing live rail tunnel. So there were high-speed, or not high-speed, trains running by every 10 minutes, basically, and on a regular speed. And we had our tunneling operation right beside it. So everything was very sensitive. Obviously, the traffic on top was going by, and we built our tunnels underneath there. We had the requirement between the drives of about 20 meters, of about 2 diameters of offset. At the end, we decided to go through with one tunnel first and then do the next one. Then we started with the final lining already on the first one. That was an operational decision. Another operational decision, we had an excavation sequence of a temporary shotcrete invert from the top heading. Originally, after we went through the first half tunnel, we said we want to accelerate. We saw we made some progress. The monitoring was performing as expected. So we went to a fast ring closure excavation without temporary invert, just top heading bench and quick ring closure, and that was equally successful then. We did that for the rest of the tunnels. Again, what you see here on the left side is some of the piles of the roof piles. They were sticking into the cross section when they got diverted, when they were pushed in. So we were cutting them out as we went. We had ring length, excavation length of 1 meter. And for every excavation length, we cut out part of the steel pipes that were reaching into the cross section because we wanted to make sure that we have a continuous thickness of the outer lining, of the shotcrete lining, according to specifications. That all went well. We also took out the cross passages. We heard already we had to install 2 cross passages for ventilation purposes. Here you just can see how small the middle pillar was. It was basically not really existent. And this is something I think that we took away. We knew before, I could say, but now we know you can do that. We don't have to stay away from the tunnels. You can do that if you do the analysis correct, if you have a designer who knows how to deal with that. We were confident from the beginning, otherwise we couldn't have built it like this way because the right of way was limited. We couldn't move the tunnel further out. So we had to put them very close and also close to the existing tunnel. It was touching the foundation, which we had to cut off sometimes. But also the existing tunnel didn't move. So the sequence that we decided to go following the recommendations of Dr. Sauer was taking care of all that. At the end, you know those pictures, membrane for the waterproofing, because when it's raining, even though it's an embankment, when it's raining, there's a lot of water coming from the road surface. The tunnel had to be watertight. We put the membrane waterproofing in and the concrete final lining. That was only reinforced at the portal areas, and in the tunnel itself it was just a fiber reinforced concrete lining. And this was all done under full operation, under full traffic from the surface and rail traffic on the site. At the end, the project was completed successfully. Some lessons learned. Going into this project, I think you saw now that it's not so easy. It wasn't so easy to go over that, to to have the confidence to be able to build something like this even. But what we have learned and taken away is with a good designer working hand in hand with the right experience, with the right people, you can do many things. You can build tunnels also with only 2.5 meters of overburden. One more detail, the overburden, we were not allowed to grout between the tunnel and the road. Yeah, that was a requirement of the highway agency, because that was one of the ideas. Let's just grout the hell out of it and then mine through. That was not possible, so we had to leave that all in place. It was all loose material, and we mined our way through. We had very effective risk mitigation measures in place for every situation. We had 2 or 3 options how to deal with that. We had some good people on site, also on the construction management and supervisory side. We had the engineer on site who had a lot to do as well, because we encountered obstructions every day. Basically, there was a whole sheet pile wall in going across the tunnel halfway through that was nowhere shown in any plans and so on. So we had to work our way through there and take these things out and still build our tunnel. Contingency planning is extremely important, and a dedicated resourceful workforce. The people really got into that project. They felt ownership and said, well, we want to get through that. We know it's difficult, and really made it through the project. And we completed on schedule. One of the first projects for Metrolinx on this corridor that was actually completed on time, even though it was the riskiest, by far the riskiest project of all the others. And Metrolinx was extremely thankful and happy for that. We were happy about that as well. Obviously, we got quite a few awards already for this project. It was really an outstanding achievement from everybody who was involved on the site. I really have to reinforce that. I think without our colleagues from Dr. Sauer, I would say I wouldn't know who else to call up for challenges like this, who would go over it and who would be able to convince a client to do a project like this. Yeah? The client was almost running away when he saw our first sketches and said, are you crazy? You can't do that, it doesn't work. Yeah? We worked through this 12, 14 months in the RFP period to tell them, to show them it is possible. We think about every step. We modeled every step, as we have seen already in the RFP phase with 3D FE models, just to convince them we believe it works. And at the end, they trusted us. Yeah, they saw that these people know what they're doing. And we were successful. One mentioning here, it's probably the shortest cross passage you have seen. It's very, very short because there's really no meat in between that we have built there. That was the easier part of the whole construction compared there. So I would just like to say thank you to everybody who was involved. Hope it was interesting for you to see. So please don't scare away if you have challenges like this. There are solutions to these. Get encouraged and try to find the solutions and go for it. Thank you very much.
Thank you very much for the interesting presentation. Are there any questions from the floor, please? Could you say your name and affiliation, please?
Hello, Steve Parker, consultant, Keystone Tunneling. Very interesting paper, thank you. Couldn't quite see some of the graphics, but the settlement, did I read it correctly that the road level settlement plus or minus 1 millimetre? One of your earlier slides, is that correct? Was it 1 centimetre?
It was 1 centimeter.
No, I think at the beginning, during the tender process, they had unrealistic settlement expectations. Right, we had this the retaining wall where we had to remove the piles. They stipulated maximum or stop work level settlements of 1 millimeter.
Yes.
And during the tender process, we tried to explain to them, and we were successful at the end, that that's not how tunneling works. That we had to do reflector-less monitoring, right? Not even our tolerance of the measurements were not 1 millimeter. We told them we will get constantly stop levels, and we didn't have a process how to restart again. So I think we had to do a lot of convincing for them to change during the tender process the settlement criteria to meaningful values. And
Totally agree.
they
what
were.
did you achieve in the end? I couldn't, again, the graphics, I couldn't see what was the final settlement or the worst settlement on the highway that you achieved.
The worst settlement on the highway was, as Gerhard said, close to the retaining walls. During the vibration of the sheet piles into the wall, they were about 60 millimeters or 65 millimeters. And we had another location where we got to a similar amount of settlement during the pipe installation with an unrecorded obstruction that caused.
But the road was kept operational.
Pardon?
The road was kept operational.
The road always was open. I think it was also for the client there a surprise, or I don't know whether it was a surprise, but to see that even if the road, right, they were of the opinion that we would create steps in their road, and a major part of our convincing was that it is a smooth trough, right? And even if there is the maximum settlement is 65 millimeters, the slopes are small, and it probably is not even perceived if the car goes over this settlement.
You obviously made your case well.
Yeah,
Thank
yeah.
you.
Hi, Arsenal from London Bridge Associates. My question is, you were fairly confident of your FE model. In the middle of a working highway, how were you able to collect samples for geotechnical investigation during the tender process? And how were you so confident of the model? And how were you able to build a shaft in the middle of a working highway? I saw it was from 10 meters wide, I guess, that section.
As you saw, the highway has a history. It started as a 6-lane highway, I think, at the beginning in the 1950s or 60s. They started building it, and they continued to widen it. They added express lanes, then the other motorway came in, and so there are pieces of median in between these lanes. One is, the widest is the one where we placed the shaft. But there were smaller grass medians in between, and this is where they, during the tender or during the conception phase of the project, they took a few samples. They didn't take all that many, yeah, the convict or how we were convinced or certain that the model would work, or that our calculations are halfway acceptable, that they would give reliable predictions, were these sensitivity analysis that Angelos described. We looked at it over a certain range, and probably thanks to the low overburden that we had, the variation in results in terms of settlements was not that dramatic with the expected variation of the stiffness of the ground.
Thank you.
Just may add that the two things were also that the parameters could not get any lower. So you cannot simulate something with less than 10 megapascal stiffness, for instance. And the other thing, as Thomas said, we checked everything. So we checked variation, we checked sensitivity of everything that could contribute. That gave us the confidence in the end to believe what we calculated.
Hi, Christoph Ebele, Mott McDonald. A question on spike concrete which you used. I recall on one of the pictures I saw a bit of mesh in the primary lining, but you used fiber reinforced concrete for the secondary lining. Could you perhaps explain a bit the considerations behind the selection of, well, mesh over fibers for the primary lining? And maybe also tell us a bit more about the parameters of the spike concrete which you selected for the project. Was it particularly fast, or were there any particular considerations on that one?
The reason why we used mesh and lattice girders for the primary lining was basically a conservative approach, and our construction director wanted it basically and didn't trust in steel fiber, and said the whole situation is so sensitive that we don't want to take any risk. And he said, when I put a mesh up, then I know what I have. Yeah? So it was more a perception than a calculation, I would say, at that point. The shotcrete was a very regular shotcrete. We mixed it ourselves with a small mobile mixing plant on the job site, basically. And so we mixed it ourselves. It was I don't know how you would call it here.
I think it was a regular 35 MPa shotcrete with quite accelerated. We had the strength development defined. I think we don't get 0.9 or 1 MPa after an hour, and with all the testing that was involved. So, but nothing, I think nothing out of the ordinary that you would see on a typical NAT or SCL
just
site.
given the time dependency which you modeled and the creep which you modeled in your really complex finite element model, did you then optimize around the spike concrete parameters as well? Was it one of the parameters which you tried to vary to limit settlements?
Are you talking about the analysis?
In terms of early edge strength gain, fundamentally.
During the modeling, no, we assumed a lower equivalent stiffness for the shotcrete to account for the strength development. This is something that we normally do by calculating this strength development process, and it worked quite well.
Okay, couldn't understand it very well, but thank you anyway. Thank you.
No, we did not simulate explicitly the creep process and the strength gain of the shotcrete in the model. So the model that we used was a non-linear model of concrete, not of shotcrete per se. And what we did, we used the lower stiffness, lower Young's modulus, to simulate this time-dependent process somehow, the strength gain with time.
Thank you.
I probably can add something to that. The issue why we didn't spend a lot of time checking the final strength is that due to the very low overburden, the stress levels in the lining were extremely low. I think from a pure stress perspective, we could have used probably a lining that is 5 centimeter thick, and it would have still met the required strength criteria, right? But for our process and tolerances, we sprayed, I think, 300 millimeters. So the stiffness difference wouldn't have probably made a significant difference in the settlements.
Point taken. Thank you.
Paul Perry from Houston Consulting Engineers. The overall project, I mean, it looks as though you undertook the lining and the tunnel works, and then there was a handover to complete it, presumably. So were there any provisions for follow-on works within your lining, fixings, details that you had to make provision for in it? And a second question, if I may, with all that instrumentation, was any left in the ground to hand over for future monitoring, almost like a sort of structural health monitoring beyond the end of your contract, to see how it performed, basically?
To your first question, the original plan was to put the catenary and the whole system into the tunnel. They wanted to first kind of have the complete thing done, but as Thomas said, there was a connection on either side, and the connections are delayed. They're still building it, so they're still not done. And then they decided not to put it in, so we put only the provisions in so that they can then later hang up the catenary and everything. So it was basically very pure concrete with a few fixtures in there, which we didn't have to do. In regard to the monitoring instruments, we took everything out. That was a requirement by the contract. So we also took out the clinometers and so on, the total stations up there, of course. So everything had to be taken out. We had some period of 1 year, which was between substantial completion and final completion, where we had to continue monitoring. and then everything was taken out.
Any other questions? Oh, okay.
Hi, I'm Jason with Robert Bird Group. I have a question regarding the pipes, the big pipes that were jacked inside. How was it monitored? And in one of the slides, it was showing that some of them bent and came inside the tunnel, and you had to cut it off. Was there a case that it went up and it was in a position to compromise the road?
I didn't understand. It was bent off, and what was the last part?
Some of the pipes came down,
Yeah.
and while you were boring it was obstructing, and you had to cut it off. No?
Yeah.
Was there a case that the pipe bent up and it went into the road?
No, fortunately not.
But how was it monitored? If I
We monitored through the center of the auger, basically. So we monitored through, and on the long stretches that went 78 meters, we actually had a pre-drill navigation rod first, and then we went with the auger over it.
Thank you.
And it's Richard Southerton from Murphy. I was just wondering, with regards to the existing tunnel there, was there any deterioration of that structure? Because they do use a lot of icing salts over there, and obviously it does get pretty cold. I was wondering if that tunnel itself was in a bad way.
We made a huge amount of monitoring in the existing tunnels. So we had all kind of instrument in there, because the client was extremely nervous, because, as I said, there were 3 tracks of trains going through continuously, which we were not allowed to interfere. And the movements at the end, they were negligible, absolutely negligible.
I was thinking more in terms of the actual sort of condition of the existing structure, as it were, and whether that has shown quite a bit of damage already, or whether it was in good condition.
There were cracks in because it was from the 60s, the structure, so that it was not a perfect structure. It was not fixed before, but we monitored the cracks and everything, so and it didn't move, basically.
Okay, thanks.
Great, thanks very much, both, all 3 of you. Shani Wallace from Tunnel Talk. Gerhard, you said that you finished one of the tunnels first and then came back and started the second one. What was the discussion about which of the 2 you would do first? You said you did the outside one farthest from the existing tunnel. And then how long did it take to get through each of them? I can't remember how long the tunnels are and their cross-section. So did you have to put the final lining into the first one before you started the second one?
Okay, a few questions. Let me see if I remember all that. The choice which tunnel to take first was taken purely on the safe side. We didn't want to be too close to the existing tunnel when we started, because it was still a kind of trial operation. The team had to get used to it. We didn't know how the ground would behave, how the surface would behave. We thought, when we do the tunnel that's further away from the existing one, then we have one problem less. We only have to look at the highway, and that was, I think, a good decision. The only requirement, I think I mentioned it from the designer, was that there's a 20-meter distance between the heading of the first and the second excavation. So there was no requirement to put in the final lining first. We excavated the first tunnel first, and then almost went through the second one before the final lining of the first one started, but there was no requirement to fix the first tunnel first before going into the second one. Excavation rates, the tunnel is 180 meter long, times 2. I don't have that in my mind right now. We usually did about a meter per day on excavation. Yeah? Sometimes there were some obstructions in there, sometimes we had to cut out piles, then it took a bit longer. So I would say, in average, it was probably between 50 and 70 centimeters per day. And the size was pretty substantial actually. It was 10.5 times 9 meters, so there were big cross sections.
I think Shane, another consideration for doing the one away from the tunnel first was this the backfill of the existing tunnel, that we thought that in case we have to treat it substantially and can't stabilize it with spiling alone, that we could do that from the existing, from the already built tunnel, and hinder the progress rates in the second tunnel less. But at the end we didn't have to do it. Spiling alone in these sections were sufficient.
Hi, Dr. Clive Shen from Gakis. I think I have the same question with the tunnel talk lady. Just a follow-up. I think what you say is the second tunnel just like 20 centimeters behind the first tunnel, so you don't really need to wait until the first tunnel lining get enough concrete strength before you start to do the second tunnel. Is that the case, what you were talking about?
I said 20 meters, not centimeters.
20 meters.
20 meters. So there should be enough strength in the first one before you go with the second one. Yeah.
So it's about a day, something like that? Or?
No. As I said, we were doing about 1 meter a day if things were going good.
20 days.
So it's 20 days, basically, more or less you get more or less the full concrete strength.
Okay, thanks.
Any other questions?
Hi everyone, Tomasz Regala from Technical Office STRABAG. I have 2 questions. First one, at the very early of your collaboration with STRABAG, how did you advise or design the model of the early contractor involvement? It was any kind of plan like that you wanted to have close collaboration with the contractor as in this kind of our UK model? And the second question, looking at the lessons learned and the risk established from the beginning of the project, what would be the most expensive sort of accounted during the construction that you can say, oh, we have not really thought about it, but that cost us the most?
I go first. I mean, the collaboration, we identified this project and thought that's a very good collaboration for us. We knew that STRABAG had the competency to build a complex project like that. They had experienced people available to do it. I assume they thought we are the competent designer to handle that, and we reviewed the bid documents, and we started discussing it internally, how we thought we can build this underpass. We didn't look so much what they showed us in the reference design. We knew they want 2 railway tracks from this side to the other side, and we brainstormed what we could do and how we can build it safely, and then more or less had a thought process how we can convince the client that they change contract conditions as necessary, that we can do it the way we thought it can be done safely and effectively. That's the process we had. I think we worked very early together with a very open discussions, constantly what we think, what elements would do or would not do, what would be beneficial and what not. Gerhard mentioned the spiles. That was at our first thought, right? We don't want to take material out by support installation. We rather push stuff in and had these discussions and managed risks and had long discussions that then came to the solution that we put. Which part was most expensive? Gerhard is probably in the better position.
Cost-wise, what cost a lot of money was the pipe checking operation. We used 3 machines basically, and we were on a schedule basically, on a tight schedule to finish the tunnel, so we had to accelerate. Also the disruptions that we went through with the pipe checks, where there were many occasions where there were boulders in there, steel pieces, wooden pieces where just the auger wouldn't go through, and we had to take the pieces out and then continue. So that was certainly a cost factor, but we had a risk budget which covered that. And the second part was going through these wing walls of the existing tunnel. That was also a tedious operation because that was in the landfill or in the fill area, very soft running ground, sand and so on. And we had to cut these wing walls out according to the tunnel, so that was a bit a tedious operation. But again, I think we planned the works well in the head, and it was done properly.
Thank you.
Sorry, just another question, if I may. In your convincing of the client, how many people were in the room when you were trying to, what was the process of convincing the client, we're going to do it this way? And to have them accept it, of course.
Well, I think it started at the contractor outreach before the pre-quals when they first contacted me and found that their proposed solution didn't work. Yeah? They said, well, we're still going to put it out, but the contractors will come back with something else. And the person on the client side, he really believed our approach with the NATM solution and said, oh, that's a good idea, that I'm sure that works, and that he actually changed the specifications to allow us to bid that option even. During the process, it was more difficult, I would say, during the RFP process. I think we two were fighting on our side, basically, against probably 10 people on the other side. The client, the advisors, the MTO, the highway agency above, who obviously had a big interest not to disrupt the highway. And the problem was that, you know, if somebody, the advisor of the client was not an ATM tunnel expert. It was a consultant, good civil consultant, infrastructure consultant, but not an ATM expert. And it was very difficult to explain what we are doing and what the effects are and how it behaves and so on. And Thomas did a really great job there, modeling, explaining the models 3 times, and he still came back, I don't believe this, and how does this work? And so it was a tedious process, but we believed in it. I think that was important, and at the end we convinced them as well to sign off on it.
Okay. I've got one question. You mentioned removal of obstacles in the 800s. How did you remove obstacles from an 800 pipe jack?
I feared that question would come.
I spent all my life in that sort of size diameter, that's why.
We did it very safely, I can say. But what it entailed, and that's why we chose 800 millimeters for the pipe, because there was, at some point, there was a 500 millimeter option on the table as well, but we said that's too small. Basically what we did, we took the auger out and put a person into the pipe with all the safety and ventilation and lighting, and also the possibility to pull him back. And they were going in on a sledge, basically, with some tools, depending what it was, and basically hand removing the obstacles within the 800 millimeter pipe.
Right.
It's not a nice operation. I wouldn't have liked to go in there. But
well, I was thinking about, you know, the UK standard is 1.2 meters.
Okay.
So.
Yeah.
We had slimmer people than me on site that fit.
Any other questions?
How much did it cost in the end?
I can tell you we were finished on time and we made money out of it. Which was a surprise to me, because this pet projects typically where you spend a lot of effort and a lot of resources go in, usually the costs are running away, but we managed really well, and at the end, as I said, we really made money on that project.
Okay. Well, I think that's all the questions. Thank you very much. Lovely presentation and a lovely set of questions. Thank you.
Thank you.
Right, we've got a few slides to run through. First couple. Earlier today we had a lunch for all the James Clark Medal winners over the years, and that's the group photo of all the medal winners that turned up for a lunch downstairs earlier today. A real good event, a lot of tunnels discussed and built and rebuilt, very much like we do in the bar after the event tonight. The other thing that happened is that Douglas Parks brought with him a picture that he had been given by James Clark's widow quite a few years ago, which is, as it says, mucking out. He's given that to the BTS. He's had it for quite a few years and he feels the best place. So he's given us that, and we are now going to discuss with the ICE as to where and what we can do with it, and if we can arrange for it to be displayed within the ICE going forward. So that is the plan. So that was very nice, and of gifting us that painting earlier today. Right, moving on to the more everyday ones. The most important one, of course, is food and drink is kindly sponsored by Dr. Sauer and Partners. Thank you very much. Next one, the BTS Health and Safety course, 20th and 21st of November. The bookings are open. Please look around your organisations at people that would benefit for coming on the course. 2 days here at the ICE. I can't remember the exact figures for the course, but it's only just over £200 for the 2 days. A lot of eminent tunnellers will be doing presentations on health and safety over those 2 days. Very worthwhile. Moving on for the rest of the year, Thursday the 2nd of November, BTS young members have got a workshop, resin injections to do or not to do. So that's the afternoon. You can book through their website. Spaces are limited on that workshop, so people need to get booking early. That's in the afternoon of the 2nd here. In the evening, the young members have their AGM and November lecture. And the theme there is, can tunnelling ever be sustainable? These are in person here. The next main BTS meeting is Thursday the 16th of November, and that's on internal ring propping Hinkley Point C offshore connections. 6 o'clock start here. Then we get up to Christmas, main BTS meeting Thursday the 14th of December, Silvertown Tunnel update, a Christmas jamboree. So that's in here on that evening as well. Finally, a slide showing where you can get hold of all the information regarding the BTS. But just a couple of minor things before we go, just an update really to everybody. We haven't got any slides tonight, but the 50th book is progressing. We are hoping to have pre-order going out in November or December. So look out for emails to be able to pre-order your copy. We are hoping that printing will actually occur in early next year, and we are hoping that we'll have a book launch here at the ICE either in April or May. That's yet to be finalised, but that is the plan. So, as I said earlier today, it's quite a large book, so make sure your coffee tables are well designed for this book for the future. There's a lot of reading and a lot of interesting items have been given by all our members, so it should be a very good document to have for coffee reading for the future. So, right, thank you all very much for coming, and see you all downstairs, and thank you very much for Dr. Sauer and Partners for sponsoring the bar down. Okay. Good.